Welcome, friends. So, we have discussed a lot on transmission line. We have seen how to calculate inductance. We have also seen how to calculate capacitance. We have also solved few problems on that. Now, we have left with some important aspects on transmission line. Let us discuss them one by one. So let us first discuss what is, what is called transposition. It is a very important term in terms of, term in case of transmission tower configuration. Now, with the spacing between conductors may be symmetrical or may be unsymmetrical. So, as long as the spacing of the conductors are symmetrical, we have no problem. But spacing is unsymmetrical, then what happens is that the inductance of the transmission line becomes a complex number. It is a very strange thing. Like where we can say that inductance can be found out to be this value 2 plus J3 Henry. So which is a very strange thing. Now this imaginary part is the very important aspect. This imaginary part, it does what? Imaginary part, it exchanges the mutual energy. It exchanges the mutual energy between two phases. So if this is the case, then due to the imaginary part, voltage distribution between three phases are not equal. VA should be one value, VB should be one value, VC should be one value. So altogether, the voltage become very imbalanced in nature. So as a result, at the receiving end, we have got unbalanced voltage, even though the sending end voltage is very stabilized, normal. So to overcome this issue, we use transposition. What is transposition? You see, this is one span of the span 1. This is another span 2, and finally we have got span 3. We used to change the special position of the phase conductors at regular interval. Like, what do I mean by that? Suppose span 1, so for span 1, phase A conductor is run. Now when enters at span 2, so this phase A conductor occupies position 2. And when it reaches at span 3, it occupies a position 3. So in this way, at each regular interval, individual conductor gets shifted and gets position change. What happens to this if we change places of these phase conductors? Then if we take average inductance of this whole tower or of this whole transmission line, then average inductance becomes a real number. So the mutual energy exchanges counterbalancing each other in nature. So if we change the places, the net energy exchange between the conductance is 0. So L average becomes a real number. So this the spatial position of the different phases is interchanged at regular interval. It is called transposition of the conductor. It is very important. Second aspect, we should look what is the position of the conductor. We should look what is the position of the conductor. Now I have solved many problems, like if we have a 3-phase double circuit line, suppose we have these 3 conductors, this is A1, this is A2, this is B1, and this is C1. And if we have another circuit, double circuit lines, so it should be C2, it should be B2, and it should be A2. This is the normal positioning of the conductors. Now, why done in this fashion? Why not this is done in this fashion? This conductor is A2, this conductor is not A2, this is B2, this is C2. It is not done normally. Okay, why? It is a normal practice. See, phase conductors should be placed diagonally opposite to each other. I repeat, phase conductors, that means A1, A2, B1, B2, and C1, C2. The rule is that they should be placed diagonally opposite to each other. Diagonally opposite to each other. Why? See, you see the formula, you know, that is L is equal to 10 to the power minus 7 ln dm by ds. And for capacitance formula, it is 10 to the power minus 9 by 18 ln dm by ds. Now, surprisingly, this ln term, this is dm by ds, this term, dm by ds, this term occurs in the numerator of the inductance and it occurs at the denominator of the capacitance. Now, for a power system, for any power system, if we have lower value of the inductance and if we have the higher value of the capacitance, it is always beneficial for us. We of the inductance and we should have a higher value of the capacitance. If we can achieve that, then it will be beneficial for us. So if you see that if we can arrange this A1 and A2 diagonally opposite to each other, then we can achieve maximum ds. We can achieve maximum ds. Okay. So in this way, if we can achieve maximum ds, so maximum ds means what? You see this ratio will go reducing. And if we see this ds is maximum, then this ratio will be reducing. So since this ratio is reducing, then inductance value will go down and capacitance value will go down, because this dm by ds term comes at the denominator of the expression. So again I am repeating, if we can arrange the phase conductors at diagonally opposite to each other, let us say we consider this is A1 and A2. Let us say this is A1 and A2, right? So we have, this is our ds. And in second case, let us say this is A2. Okay, so this is, we have ds2 and this is ds1. So out of these two, you can understand one thing, ds2 is greater than ds1. So we can achieve maximum self-distance if we arrange phase conductors diagonally opposite to each other. So if we can arrange phase conductors diagonally opposite to each other, it will increase ds. So if we can increase ds, what will be happening? Or if we can achieve maximum ds, what will be happening? This dm by ds ratio, this ratio will go down. So if this will be go down as inductance is directly proportional to this dm by ds, as this ratio is going down, so inductance value will be also going down. And secondly, as the capacitance is inversely proportional to this ratio dm by ds, so as this ratio is going down, capacitance is going up. So to achieve low value of inductance, and high value of capacitance, we always achieve, or we always consider, or we always place the same phase conductors diagonally opposite to each other. This is very important. You should remember. So we should place the same conductor, same phase conductors of two different circuits diagonally opposite to each other to have low value of inductance and high value of capacitance. Lastly, we have got a very important term, it's called bundle conductor. What is bundle conductor? Suppose we have a standard conductor like this with radius r. We have another similar standard conductor of radius r. Now this will make one phase. That means a particular phase, suppose let us say a phase, we have two subconductors. Okay, we have two subconductors. The second diagram, we have three subconductors. Similarly, we have four subconductors in this diagram. Okay. Now, for this separated by a distance of d. Now for three subconductors case, each conductor is placed at the vertex of an equilateral triangle, side length being d. And for fourth subconductor case, each conductor is placed at the vertex of a square, side being d. Okay. Now why should we adopt this? You see, for a 400 kV or 765 kV transmission line or some other lines as well, this is a very extra high voltage existing. Now those transmission lines are operated in open atmosphere, so it is highly vulnerable, or it is exposed to atmospheric condition like lightning strike. So if a lightning strike comes, then high voltage stress may become very high. What is stress? High voltage stress, it's voltage per unit distance. It is high voltage stress. Now, as the distance is relatively bigger as compared to a single conductor case, then this D goes high. So the electric stress on this conductor as a whole will reduce, because this D has some value, finite value, as compared to a single conductor. This is the main reason. Now, for three subconductor case, you see this D is placed, so this having some finite D, making this electric stress limiting to a lower value. So, on using the bundle conductors, we can reduce the electric stress, we can reduce the electric stress on conductors, This is very important. Secondly, the effective GMR will increase. How? Now, conductor case, for this two conductor case, what will be GMR? Or rather DS. For this two conductor case, what will be the effective GMR? For this two conductor case, we have DS, that is equal to D. So you should take the square root. So this is the GMR of two conductor case. While you have the when you have the single conductor, you but when you have the bundle conductor, your GMR is increased by this term root R. Of course, if you calculating inductance, you should use R dash. Okay, but I am writing general term. So for three conductor case, what will be DS? There are three terms, so you should take cube root. So one conductor is R and rest is this one D and another D. So it is D squared. So this is becoming D square into R. Case conductor case is effective GMR is this value. We have terms. One is R. So for this term it is R. So for this to this it is D. To this it is D. And for this to this it is. So we have D into D into root 2D. So we have fourth root 2 into R dq. So effective GMR is increased quite a bit as compared to a single conductor. So these bundle conductors are very important. So bundle conductors are very important. Bundle conductors are very important. What it does, it's actually reducing the stress on the conductor. Secondly, effective GMR or DS increases. And lastly, in order to, if you use the bundle conductor, it can transfer a bulk amount of power. It can transfer bulk amount of power as compared to a single. So these are the advantages of bundle conductors. Now we have reached at the last of this module. So we need to summarize what we have learned. So first we have found that we have first seen the inductance calculation. There we have seen inductance is evaluated as 2 into 10 to the power 7 ln dm over ds, where in case of inductance calculus you should always use R dash, which is equal to 0.7788 into R. In case of a capacitance calculation, the formula being derived was, in case of a capacitance calculation, the formula being derived 10 to the power minus 9 by 18 ln dm by ds. Now you must write, or you must use R, not R dash in case of a capacitance calculation. Third, what we have seen that if we use bundle conductors, it is always advantageous because it will reduce the stress. Effective GMR will increase and it can handle okay. Moreover, we have seen conductors positioning the conductors. They should be placed diagonally. Same phase conductors should be placed diagonally to each other. And lastly, we have seen transposition is done. Transposition is done in order to have uniform voltage or balance voltage. You can say balance voltage at receiving end. Okay. So with this, I conclude this module, that is the transmission line parameter. I hope you will find this very helpful for your preparation. And from the next lecture, we will start our next module, that is the performance of the transmission line, where we will see the classification of the transmission line, different types of transmission line, how they are modeled, how voltage and current wave behaves in a transmission line, and lastly, power flow through the transmission line. With this, I am ending this lecture here. Thank you.